Hello everybody and welcome back. Today we are going to be continuing our exploration of astronomy. Yesterday you should have finished your Big Bang Theory timeline and kind of just got an idea of how the universe started, and then that idea of the hierarchy of the universe, with the universe being the largest and then going all the way up to those comets and meteorites that are actually the smallest in our universe. So today we're going to continue and we're going to understand the components of the Big Bang Theory. So now that we know what it is, we're going to dive a little bit deeper and kind of talk about the origin of our universe. So let's go ahead and get started. So you should have your interactive notebook slides that you've downloaded, and this is where we're going to start with your guided notes. So what is astronomy? At this point, you guys have had this for 2 days in a row, so we should understand that astronomy is the study of the universe, the stars, the planets, and everything in it. Okay? So if you are an astronomer, you're studying the universe itself, the stars, the planets, and anything that's in space. Okay, so astronomy is the study of outer space. That's all well and good, that's great, but what exactly is the universe? The universe is all matter and energy in space, and there's a lot of it. Okay, so when we say the universe encompasses everything. So how can you actually see all of that? There are actually satellites that are able to see into the night sky and to space, and then we do have very large telescopes. There's one in particular called the Hubble telescope that's able to see galaxies beyond ours. And really just with new technological advances, we are able to use these telescopes to see into space, and we're able to observe pretty far out. We can't see the whole universe. There are certain places that our technology we just can't reach. So we don't know exactly how far out everything goes. We don't know what all is out there. We've never been able to see the edge of the universe, but we can see a chunk of it, which is really cool. So let's talk about a light year. So here's a picture of Buzz Lightyear here. Remember, he was the little spaceman from Toy Story. A light year is actually a unit of distance. It's not a unit of time. So when you think about a year going by, normally we think about that as a measurement of time. But a light year is actually a measurement of distance. It is the distance that light travels in 1 year. So a light year, or light travels at 299,792,458 meters per second, okay? And that's converted to 186,000 miles per second, or 6.71 times 10 to the 8 meters per hour. That is fast, so fast. And you know that light actually travels faster than sound. That's why during a thunderstorm, you will see the lightning before you hear the boom from where it hit the ground, because light just travels faster. Our galaxy, so a galaxy, the definition is just a group of stars, dust, and gases that are held together by gravity. So yesterday we talked about the formation of our Milky Way galaxy and that spinning of dust that came into a cluster to form the galaxy that we know today. So it's just held together by gravity. And it's amazing to think about our entire lives, our planet, everything that we need to sustain ourselves and support ourselves as human beings. We exist in this swirling ball of dust and gas. It's pretty amazing. And again, we are in the Milky Way galaxy. So here's our galaxy again. So here's the middle, right? We talked about the middle of that nebular bulge. And then here is our sun. Our sun is 26,000 light years from the center of the galaxy, which is a long way. Anytime we talk about light years, we're talking about very long distances, really long distances. And also a fun fact, when you look up in the night sky, because the stars that we see are so far away, the light is traveling towards our galaxy or towards Earth to where you can see it. You can actually see the light of stars that have died a long time ago because it takes so long for the light to actually reach where we can see it that the stars have already burnt out. It's just that the light is still traveling through space. If that gives you a perspective on how much time it actually takes for, or how far away something is, because light travels very quickly, but even though it does, it takes it a long time to get here because of just how big space is and how far apart everything is. So in terms of our Milky Way galaxy, here's our sun, and then you or we are about right here on Earth. And remember, we are the third planet from the sun. You don't have to write anything down for here, but this is just an image of an elliptical galaxy. And when we say an elliptical, we're talking about an oval shape. So this would be a galaxy that's formed in kind of an oval pattern. An irregular galaxy here is just kind of what its name suggests. So the pattern is kind of irregular. It doesn't have a distinct shape to it. This is still a galaxy, but it's not kind of like a spiral or an oval the way that our galaxy is. And then a galaxy cluster. So remember, we're in a cluster of about 40 galaxies, and those are galaxies that tend to just be close to each other. So here's 1, 2, 3, 4, 5, 6. Probably be one over here, 7, 8. And then these smaller ones could potentially be galaxies too. So these are galaxies that are just clustered close together. And then here is Hubble's law. So Hubble was an astronomer. That's what he's who the Hubble telescope is named after. But Hubble's law basically says that the universe is constantly expanding. And we know that from yesterday too. When we talked about the Big Bang, we found out that our universe started as a single point, a single origin, and then expanded outward. And it's still expanding. Our galaxy is moving away from the point of origin. So Hubble's law, we do need to know Hubble's law again. Hubble's law says that the universe is constantly expanding. And again, this is an image of our Milky Way galaxy, and you are here. We are on a teeny, teeny, tiny point of our galaxy. For Hubble's law, we can use something called the raisin bread dough analogy. So if you guys have ever made homemade bread, or you've got, your mom or your grandma makes homemade bread, here's an example. So if this is our original universe here, we've got this raisins in dough, right? So the raisins would represent the galaxies, and then the dough would represent the universe itself. Well, we know that if dough is allowed to sit, it will rise and expand. The universe is doing the same thing. So even though those galaxies are initially clustered together, because the universe is expanding, eventually they will move apart and be a further distance apart from one another. And we should have seen that in the warm-up video that we watched today as well. Some evidence that we have that our universe is expanding is something called the Doppler shift. And this is just a change in color that shows how the universe is moving. So what we mean by this is that basically light exists as a wave. And there's something called the electromagnetic spectrum. And I don't want to get into much of a deep dive into this because I don't want to confuse you guys. But basically, depending on if a galaxy is moving closer to you or further away, the wavelengths that are emitted from the light will change, okay? And the wavelengths are actually determine what color it is. So what we need to know is something called a redshift. Basically, if a galaxy is moving further away from us, it'll tend to give off a red color. So when we observe galaxies with the Hubble telescope or other large telescopes, a lot of the galaxies that we see give off a red color. And the reason for that is because they're moving away from us, and the change in the wavelengths of light being reflected are causing it to have a red color. So that's the red shift. Now, a blue shift is the opposite. That's where if something is coming towards you, it's going to have a shift to a lower frequency of wavelength and then appear to be blue. Okay, so the red shift is what gives us evidence that the universe is expanding because different galaxies that are moving away appear red. Amazing, right? I think it's pretty amazing. So then our Big Bang Theory that we talked about yesterday. This occurred 13.7 billion years ago, so a really long time. A billion is a large number. Think about Jeff Bezos, who's a billionaire. He has more money than like I could ever imagine how to spend. So a billion is a lot. It's a lot. So the Big Bang Theory was, or the Big Bang Theory, the Big Bang itself was an expansion. Again, we talked about this yesterday, so you guys should remember. It was an expansion, and basically it's led to an expanding universe. The universe itself is still getting bigger and bigger and bigger. It keeps moving outwards. So this is just going to go over some vocab. And you guys have been working on your vocab, so you should recognize some of this, but we're going to hit it today to make sure that we all understand these terms. So a solar system is a group of planets, comets, and other bodies orbiting a star. Okay, so in our solar system is comprised of our sun, and then our planet Earth, as well as the other planets that also revolve around our sun, and our moon as well. Okay, and then the moons of the other planets. So solar systems are composed of the planets, the comets, and the other bodies that orbit a star. Our solar system has 8 planets, asteroids, and moons. Also comets and dust as well, but we'll find dust all over the universe. A satellite is a body that revolves around a planet. So our moon is a natural satellite, and then you can have artificial satellites as well. So satellites that they put up for like cell phones and stuff like that, those are artificial satellites, but they're still a satellite because they orbit the Earth. And then our moon is a natural satellite. It wasn't man-made, but it still revolves around the planet, so it's a satellite. The axis of Earth is the imaginary line that goes through the center of the Earth, and it does have a tilt. And we'll talk about that tilt a little bit later and why it's important. But the tilt of Earth is at 23.5 degrees. So Earth is not straight up and down in Earth. It does have a tilt, or in space. It does have a tilt to it. Rotation is just turning of the Earth counterclockwise on its axis. So our Earth does turn counterclockwise, and when it rotates, it is just spinning on its axis in that counterclockwise direction. And a revolution is traveling around a center point. So Earth revolves around the sun, okay? So Earth rotates on its axis, and then it revolves around the sun. And then our moon revolves around the Earth, okay? So we rotate on our axis, we revolve around the sun. And then we revolve at 1,600 kilometers per hour, which is what creates the time zones. So a day is the length of time it takes for one rotation. So again, we rotate on our axis, revolve around the sun. And then one day is 23 hours, 56 minutes, and 4 seconds long. And an orbit is just the path an object takes around another one. So if we orbit around the sun, the path that we take around the sun is our orbit. And an elliptical pattern is an oval pattern. So if we say that something has an elliptical orbit, it's oval patterned. And how long is a year? 365 days, 6 hours, 9 minutes. So 365.26 days. So what do we do with the extra time? Every 4 years, we have to have a leap year, which adds an extra day to the calendar.